Welcome everyone, and thank you for joining us for today's webinar, Simplifying Peptide Synthesis and Production Through New Innovations. My name is Gabrielle Ducharme, and I'm the Life Science Marketing Specialist for CEM Corporation. Just a bit of housekeeping before we begin. If you have any questions during the presentation, please type them into your GoToWebinar control panel. We will have time to answer all questions at the end of your presentation. This webinar will also be recorded and will be available to view on the CEM Corporation's website following the webinar. Now, I'd like to turn the mic over to our presenter, Michael Carney, the CEM Life Science Product Manager. Michael?
Thank you for the very kind introduction, Gabby. My name is Michael Carney, and I'm the Global Product Manager here at CEM, covering all life science products for synthetic chemistries. Today, I'd like to talk about some steps that can be taken to simplify the peptide synthesis process and really improve production through new innovations from CEM chemists. As an overview of the agenda, we'll begin with a review of the existing high-efficiency SPPS methodology that we developed in 2013. We'll continue on to new synthetic methodology innovations, which look to really optimize peptide coupling at elevated temperature and use this as a general process for peptide synthesis, so a very robust method that can be used no matter the sequence. And we're going to demonstrate the utility of this methodology with a synthesis of a number of pharmaceutically relevant peptides. Finally, we'll conclude by taking this new innovative methodology and applying it to SPPS production to maximize the benefits of fast peptide throughput for high-throughput labs and also multi-gram scale-up to access grams of peptide in a matter of a day. First, a little housekeeping. Just want to mention that, for your information as the viewer, every chromatogram in this presentation was actually performed on the UPLC system seen here. We use a Waters Acuity H-class UPLC with mass spec. The solid phase, or rather the stationary phase, and the mobile phases you can see here, along with flow rate and the temperature that we use on all columns, to provide a standardized method and also a high-quality separation method. Any peaks are integrated via MassLink software. This confirms that we have a consistent integration threshold and high reproducibility of data between multiple chromatograms. If you're interested in our overall method that we use, the gradients can be seen here, a shorter 6.5-minute method for standard peptides, and then for longer peptides, we use a longer 20-minute method. Now let's begin with, the current status or the current view that many people had for microwave solid-phase peptide synthesis after the first generation of instruments about a decade ago. It was seen that this technology can be very, very useful for difficult peptides. There are many hundreds of synthetic examples showing synthesis improvements for a wide variety of sequences. Even very challenging sequences, as long as 100 amino acids or even longer, have been synthesized using this technology. Now, there has been a dramatic improvement in reducing the cycle times as compared to room temperature syntheses. However, at the time, this is about, again, 2004, 2008, peptide synthesis, microwave peptide synthesis rather, was not really considered a high throughput format in the sequential process that was carried out. In addition, onium-based activation using HBTU, DIA, or phosphonium activators, they were typically sensitive to a lot of side reactions. And so these base-catalyzed side reactions would sometimes reduce overall target purity for a peptide. Now, in 2013, CEM released and published their new methodology called HESPPS, or high-efficiency solid-phase peptide synthesis. And this was based around carbodiamide activation. Now, we saw as compared to onium salt activation using DIC, or that was our preferred carbodiamide activator, it would provide higher purity of peptides, reduced epimerization levels, reduction in gamma-lactam formation for arginine, so again contributing to higher purity for arginine-rich sequences, and also the elimination of guanidine capping, which is very problematic for HBTU and other uranium activators. Now, I'd like to start by focusing on these 2 points here. The fact that carbodiamide activation really offers dramatic advantages when it comes to reduced epimerization and also reduced lactam formation. That's because both cysteine and arginine, the 2 residues that we're primarily concerned with when it comes to these points, they have specific side reactions that occur during coupling because of HBTU chemistry. First, taking a look at cysteine. This is a problem, the cysteine epimerization that can occur resultant from the activated form of cysteine when a base is present, so something like DIEA in your coupling solution. The amine base can easily abstract that proton, the alpha proton that's on cysteine, resulting in the enol and then addition of the proton from either face of the molecule, resulting in possible formation of the D isomer rather than the desired L isomer. In the case of carbodiamide coupling, there's no DIA present. So since there's no base, there can be no abstraction, and the polymerization levels are limited. We've demonstrated this through a number of different syntheses. Here in this example, we show with the ABC20mer successful synthesis of the sequence with both HBTU chemistry and DIC chemistry. And so even room temperature uranium couplings result in a rather high D isomer excess. As soon as you start increasing the temperature for your coupling, you see that while the reaction time drops, the overall formation of D isomer increases, which is undesired. Switching to carbodiamide chemistry, again with no base present in your coupling solution, there's a dramatic reduction in formation of the D isomer below even room temperature levels for uranium activation. Here, you get the advantage of even performing at high temperature, so for difficult couplings, you get to proceed without any kind of difficulties. And you get the dramatic rate reduction in terms of the overall time required for coupling. Taking a look at the arginine residue, here we see the issue is lactam formation. So at a high pH, the delta nitrogen of the side chain is very nucleophilic and can cyclize, resulting in removal of the OET activating group and formation of an inactive six-membered lactam. At a lower pH, so the more acidic coupling environment of carbodiamide chemistry, that nitrogen is actually less nucleophilic. The end result is that since it's less nucleophilic, there is a suppression of this lactam formation, and so you have more active arginine esters that can couple onto your peptide chain at any given time. We demonstrate that here in the synthesis of the ABRF 1992 sequence. So here, comparing HBTU chemistry at 90 degrees and DIC chemistry at 90 degrees, we see much better crude purity, the chromatogram pictured here, seen with carbodiamide chemistry. Again, this is something that's not exclusively, but definitely in large part to the fact that arginine can be coupled on much more easily, and then as a result, you have a higher purity of your actual synthesis. Putting together those benefits, so this higher temperature 90-degree coupling, rapid deprotections as well, and some other modifications to the washing procedure, we developed this high-efficiency SPPS methodology, as I said, in about 2013 and published in 2014. So I direct your attention to the paper reference on the bottom. This Orgelat paper will give you an overview of all the types of modifications and improvements we performed a couple of years ago. And this table gives just an example of some of the wide variety of sequences, varying length, varying difficulty, that are all synthesized with great crude purity, very, very rapidly, and with much less waste than any other process at the time. So more recently, we've actually vetted this technology with some very, very difficult sequences, so much longer and even more difficult than the beta amyloid pictured in the previous slide. So here in this example, we synthesize ubiquitin, a 76mer, so effectively a protein, on the 0.1 synthesis scale using standard high-efficiency methods. We simply double-couple residues after 30. That's it. That's the optimization that we actually perform for this peptide to actually isolate a clear product peak in this chromatogram. And you can see actually that we also synthesize this peptide very, very efficiently, producing only 2.2 liters of waste very quickly, less than 10 hours synthesis time, and also cleaved in only a half hour. So the whole system, or the whole peptide rather, is synthesized completely start to finish in less than 10 hours. Here in this next example, we show the AS48 peptide. This is a 75mer, and this is actually a linear bacteriocin precursor. So the JAX paper on the bottom, we actually synthesized this linear sequence for the TAM group at Nanyang Technical University in a collaborative effort for them to then cyclize it with a unique enzyme that they had isolated. And so this linear sequence was created with producing only 2 liters of total waste, just under 7 hour synthesis time, and only a half hour required again for cleavage. This methodology, again, we used standard HESPPS methods, nothing special, not even general double coupling or unique reagents, and we can again see a clear product peak. This final example of aprotenin, here's another, here's a pharmaceutically relevant sequence here, produced on slightly smaller scale, so 0.05 synthesis scale, and we can synthesize this peptide again very rapidly, less than 7 hours for synthesis, with about 1.6 liters of total waste. So since 2013, what we've done is we've looked to modify our existing technology and make it even faster and even higher purity. So the goal here with our Carbomax coupling technology, which we first announced last year, is to promote even faster coupling and correspondingly improved purity of peptide. The goals of reducing epimerization versus standard carbodiamide chemistry, that's another kind of a focus for us, realizing how important epimerization levels are for pharmaceutically relevant compounds. And then also stabilizing acid-sensitive linkages, whether they be phospho groups, glycos, or other acid-sensitive linkers, at high temperature to ensure a robust and powerful universal method which can be used for coupling at elevated temperature. The goal here is to eliminate any type of real optimization that's necessary beyond simply double coupling or using a lower loading, higher swelling resin. So this synthetic methodology I'd mentioned we call Carbomax, and it's based primarily around carbodiamide chemistry, as you could imagine. Now, the first tenet of this improved coupling method is the use of greater than an equivalent of the carbodiamide. So the goal here is faster generation of the O-acylisyrurea and also reduced epimerization by having it in this active form for a smaller period of time. The second tenet of this method is the addition of a small amount, so less than 0.4 equivalents of base. This would be DIEA. That it seems a little counterintuitive to add something that's alkaline to your acidic coupling mixture, but this actually increases the second step of the reaction, the acylation rate of the coupling reaction, that is, and also helps to stabilize acid-sensitive linkers that can be prematurely cleaved by the acidic nature of carbonamide coupling chemistry and the oxima or HOBT used. Now in this diagram, we see the two steps which are really accelerated by this Carbomax chemistry. First step here is formation of the O-acylisyrurea by using more than one equivalent of carbodiamide. We promote this reaction to drive it forward much faster. After conversion to the oxima ester or OBT ester, depending on what is used as a supplementary coupling complex or coupling reagent, addition of a small amount of DIEA can accelerate that final acylation step to form your peptide bond very quickly and efficiently. In this slide, we demonstrate the utility of this increased carbodiamide activation strategy for a number of syntheses of pharmaceutically relevant compounds. In all cases, we either see comparable purity or an improvement in purity over the existing high-efficiency method. Specifically, we're going to take a closer look at the thymosin A1, meganin 1, and also liraglutide sequences. Now, these are all relevant for pharmaceutical applications. Thymosin is important for hepatitis B and C. Meganin is important in antimicrobial applications, and liraglutide in diabetes research. But we'll take a closer look at the improvements to purity as well as the goal of suppressing epimerization. In this first example, the title sequence is synthesized with both the increased DIC method and the standard HESPPS method. Comparing the two chromatograms, it's clear that there is a reduction in impurities and byproducts that are formed from the synthesis, and the end result is a higher purity sequence just from this simple step. Now, to take a look at the epimerization levels, what we wanted to do was examine a difficult sequence like thymosin. So here we see another great high purity synthesis, very clear product peak. And what we actually did was take our sample and send it out for CAT analysis at a company, CAT GmbH in Germany, who takes the crude peptide, they hydrolyze the sequence, and then they introduce the monomers into chiral GC analysis to collect data. And so from this chiral GC data, we can see very, very low epimerization levels for all isomers, or for all residues rather, in the sequence. In this next slide, we take a closer look at liraglutide. So this is a very important pharmaceutically relevant sequence. And here we see, again, the advantage of using increased carbodiamide concentration, or increased DIC concentration in this case, to see an improvement from the HESPPS sequence on the bottom Switching to the top, we see a reduction in all impurities for a much, much cleaner baseline as compared to the bottom syntheses. So this work was actually done, we get a lot of inquiries about this, it was done on a 0.33 millimole per gram Wang polystyrene resin. And we've been very aggressive on the integration because we want to ensure we're capturing all impurities of this sequence. And this high purity synthesis is definitely validated through the clarity of the mass spec in this case, very, very clean. Taking a look at epimerization levels, again, we wanted to compare our existing high-efficiency method to this improved Carbomax method. And in just about all cases, we either see maintenance of the epimerization level or reduction in about 75% of the cases, reduction of epimerization to an undesired isomer. Now, one residue which isn't documented here and is especially problematic is histidine. So I've highlighted it here, and we'll actually discuss that in the next slides, as we had an opportunity to improve the SPPS process even further by taking a close look at the histidine residue. Now, histidine epimerization isn't a coupling reagent-specific problem. It's specific to the residue. It's an intramolecular process where the pi nitrogen of the side chain can abstract proton to lead to the enol, and then again, addition of the proton can happen from either face, resulting in either L or D histidine. Now, because this is an intramolecular process, again, it can be a little bit harder to limit. It's possible to do it through different side chain protecting groups, and one that we've found is extremely effective when it comes to high temperature coupling and suppressing epimerization is the His-Bach derivative. So actually using a Bach protecting group on the His side chain, this is actually located on the tau nitrogen, not even the pi nitrogen. This side chain effectively has a very strong inductive influence on the electrons of the pi nitrogen. As a result, we see a dramatic reduction in formation of the undesired D isomer. In the bottom entry, it's clear that even at an elevated temperature of 90 degrees C with a rapid 2-minute coupling, histidine epimerization is limited to less than 1%. So from the data in this table, we wanted to take a more critical look at histidine isomerization with this ABC20 mer sequence seen here. First, we started with room temperature HBTU coupling to establish a baseline in which we saw about 2% formation of D isomer, even at room temperature. And as we expected, switching to carbodiamide coupling suppressed this isomerization a little bit, down to about 1.5%. However, as soon as the temperature was increased to accelerate the rate of the coupling reaction, we saw an increase up to about 7% formation of D isomer using the His-Trittle monomer at an elevated temperature of 105 degrees. Switching to the His-Pi M-bomb monomer in entry 5, we still saw that there was a significant level of D isomer formation, about 3%, but using the His-Bach residue with that strong electron withdrawing characteristic of the Bach protecting group, we were able to, at 50 degrees, suppress isomerization below 0.5%, and even at an elevated temperature, so pushing the limits up to about 105 degrees for coupling with a rapid 1-minute coupling, we were still able to limit D isomer formation to about 1%. So almost half what you can see with a His-Trittle residue, even at room temperature with HBTU coupling. So shifting gears a little bit, let's take a look at how this carbodiamide activation strategy handles acid-sensitive linkages. So in this case, we're going to take a look at phosphopeptides. And these are sequences that are prone to a number of different side reactions. Beta elimination can occur during deprotection. This is particularly problematic when it comes to phosphoserine sequences, and especially at elevated temperature. Again, this accelerates all reactions, even undesired ones. Second, we'll take a look at the acid sensitivity of the phospho linkages. So this is something that can be very problematic with carbodiamide chemistry. The phospho groups can easily pop off because of the acidic nature of oxima. It actually causes that dephosphorylation. And again, this is accelerated at elevated temperatures. Plus, it can be difficult to couple consecutive phospho residues in a single sequence. And what we've seen is that actually with this Carbomax chemistry, we can dramatically improve it. So the first chromatogram you see, this is based in our standard HES-PPS methodology. We are using double DIC to try and get faster acylation or faster oacyl isourea formation. However, we still have problems with phospho groups popping off and creating this large hump with no real discernible product peak. By simply adding a slight low equivalency, so 0.4 equivalents of DIEA to our coupling solution, we can complex excess oxima that reduces the overall dephosphorylation of the peptide sequence. As a result, here we can see clear, discernible product peak out of what was previously an unintelligible mound of peptide byproducts. This stabilization is also useful for glycopeptide sequences. So in this case, we're going to take a look at the MUC1 analog. Then when it comes to glycopeptides, it's extremely important to use low equivalents because of the high cost of the residues. And so not only do you want to ensure that you get efficient coupling so that you're effectively using your expensive reagents, but you also want to prevent that removal of the O-linked residue because of the because of the acid-sensitive conditions of the sequence. And so in this example, again, we see that our Carbomax methodology using a little bit of DIEA performs stupendously, really. We can see a clear product peak, and most importantly, we also only use 2 equivalents rather than the standard 5 equivalents of our glycoamino acids. So we ensure that it's going to be a cost-effective methodology and also one that, again, is very robust, can be used for a variety of different sequences. And so this peptide was actually made in only about 3 hours' time, very, very effectively with only about 500 mils or 600 mils rather of total waste produced. So we can see that we can make a difficult sequence very, very quickly and also very effectively with this methodology. So to kind of sum up our current innovations when it comes to chemical methodology, we see that carbodiamide activation really offers some major improvements over ammonium salts at elevated temperatures. First, we've seen that we can increase the product purity simply by adding an excess of the carbodiamide, DIC, in many of our cases. And second, we see that we can stabilize acid-sensitive linkages by addition of a slight amount of DIEA. This is something that's very important for a number of sequences out there and for robustness of the method. Now, in addition, the benefit of this entire protocol is that we also see reduced epimerization levels across the board for all residues, and by utilizing the His-Bach residue specifically, we can also reduce His epimerization down to less than, in many cases, amino acid residues of any other part of the sequence. So as a result, all 20 standard amino acids can be coupled on at a single high temperature. We've pushed this up to 105 degrees C. And really, we have created a powerful universal coupling method at elevated temperature, which requires little to no optimization. Now, our next step is to take what we've learned, this chemical methodology, and apply this to maximizing our benefit for SPPS production. And to do this, we want to accelerate the rate of peptide synthesis to really an ultra-fast pace, something that is capable of suiting any production need. And to do this, what we're going to do is take a look at using some methodology that we developed for the high efficiency process, in which we do not wash after coupling. We immediately introduce deprotection solution. And instead, what we're going to do is create a one-pot process where we add our deprotection base directly to our coupling solution. So this offers a number of advantages. First of all, there's no drain time associated with this step. There's no new solvent, so it's more efficient in that respect as well, using less solvent and producing less waste. Plus, there's no temperature ramp time. There's a shorter deprotection time because the bulk solution is already at an elevated temperature for the deprotection step. By reducing the concentration of deprotection base, we can also limit the amount of washing that's necessary. So a lower concentration will require less washing, and we can push the reaction forward by performing our coupling step and our deprotection step up at an elevated temperature, so 105 degrees, a 1-minute coupling to provide the best results. And to combine this method enhancement with the chemical methodology enhancements, we do this with our system, our newly released system, the Liberty Prime, and this is really the best way to maximize SPPS production. The Liberty Prime system consists of the Liberty Prime module, a microwave reactor with reaction vessel. Then over on the side of the system, we have an auto sampler or resin transfer module, which can handle up to 24 positions, and a dedicated pump module, which ensures accurate and fast delivery of reagents. So taking a closer look at the Liberty Prime, the amino acid reservoirs specifically have their amino acid stock solution stored at a high concentration, 0.5 molar, which is stable for about 1 week. And so this is something that is, for most production labs, they won't even last that long. We have a wide variety of vessel sizes that are available for storage, either 50 mil or 120 mil. So that covers a wide range of different syntheses and 27 different positions, which can be used interchangeably for a wide variety of different residues. Every amino acid is delivered by our FlexAdd technology, or patented FlexAdd technology, which means that you can add just about any amount without any kind of calibration. No calibrations are necessary for this liquid addition methodology, and it doesn't use optical sensors or syringe pumps, so it's not prone to the typical problems associated with this hardware. We see that for the scale range of 0.1 up to 0.4 millimole, we're using low excess, so 5 or 4 excess at the larger scales, and low volumes of addition of reagents, either 1 to about 3 mils. Your activator, DIC, is delivered through, housed in a 500 ml pressure-rated bottle, and is also delivered by FlexAdd technology, again with no calibration necessary. Now, the beauty is that for a wide variety of scale ranges, from 0.1 to 0.4, you can mix and match whatever different sequences you're doing, because about the same concentration is used. So we use 4 molar concentration of DIC for larger scales. 0.1 uses about 2 molar. But simply when running a small scale, if you're running a 0.1 synthesis along with other larger syntheses, it's easy to just double, use 4 molar instead, double the excess, so that you can run these scales interchangeably. Now, the heart of the Prime system, in addition to the new capability of addition through the amino acid manifolds, is actually the pump module seen here. So this pump module is responsible for pre-calibrated, non-pressurized delivery of deep protection, oxima, and wash solvent. So again, there's no calibration necessary for addition of these reagents at all. So at this point, nothing that you add to your reaction vessel for coupling or for deep protection, for washing any part of the SPPS process, none of it requires any type of calibration. And since it's a non-pressurized container, it's easy to just open these reservoirs whenever you want. You can refresh solutions during a run. And these pumps are calibrated to provide precise delivery of quantities as low as a quarter mil, so 0.25 milliliters, various increments. So it's possible for them to deliver reagents very, very quickly and very accurately. Now, the resin loaders that are housed on top of the pump module, these are necessary for rapidly moving peptides from the resin loader position to the reaction vessel as part of a queue in an automated batch. So this is something that's a fully validated transfer process with both certificates of line clearance to ensure that there is no cross-contamination, and also validation to ensure that there is no cross-contamination between multiple different positions, since there's a common flow path used. Now, the larger option for 0.5 millimoles, so for people that are looking to make a little bit more peptide, it's possible to use a larger optional RV, so 50 mil instead of our standard 30 mil RV. That would be their reaction vessel. And you can use 120 ml resin containers instead of our standard 50 ml resin containers. So again, the same system can easily be scaled up from 0.1 up to 0.5 millimole syntheses. So the end result for the Prime system is that it's really a flexible system in which you can intermix multiple different synthetic scales, easily run up to 24 peptides unattended in a completely automated fashion overnight, and use the 27 available amino acid positions for a wide variety of different reagents. All peptides that are in queue can be removed once they're finished. If you want to add a new peptide to the queue while the system is running, it's possible to do that. So it allows a lot of flexibility from multi-user labs, where one chemist might want to walk up and start something before they leave for the night, and then a chemist on a later shift can actually queue up their sequence as well while the other peptide is running. In addition, this is a very reliable system. As I'd mentioned already, all the reagent additions, anything that's added to the reaction vessel is pre-calibrated. And so that means that there's no maintenance required, nothing at all. In addition, we've optimized the short flow paths for quick and efficient delivery and draining, ensuring that there's no cross-contamination between multiple different positions. So to put it all together, this rapid methodology, the Carbomax developed methodology, and then the enhanced one-pot coupling and deprotection methods of the Liberty Prime, they result in a very, very rapid cycle time, so only 2 minutes and 10 seconds on the 0.1 scale, and even faster than 4 minutes, so only 3 minutes and 50 seconds on the 0.4 scale. So you can scale up effectively very, very quickly, and again, using a very low amount of waste. Only 8 mils of waste is produced per cycle for 0.1, and 25 mils of waste for the 0.4 scale. Now, as you can see on the bottom, overall cycle uses the coupling solution of the previous step, in which and then deprotection, concentrated deprotection is added to that already warm coupling solution. That's that one-pot coupling and deprotection step. After the deprotection process proceeds, there's a drain, a single wash is performed, drained again, and then coupling solution is added for coupling on your next amino acid. And that's something that I definitely want to address. I want to take a look at this one-pot coupling and deprotection step and address the concern of insertions, because that's something that typically, this is something that peptide chemists are worried about is well, the problem about adding deprotection solution, and not ensuring that your coupling cocktail and your activated amino acid ester from the previous step, if that's not removed, you'll run a risk of insertion. But there's really no risk of insertion with this process based on the rates of reaction of your desired and undesired reactions. So what you want to do by adding straight deprotect to your coupling cocktail is immediately quench all of your active ester from the previous coupling step. And this is actually what happens. The liquid phase quench here, the rate of reaction K1, which results in deactivation of active ester from the previous coupling step, that happens orders of magnitude faster than this second diagram. The two-step process, both also solid phase processes, so they're slower than the liquid phase process. K2 and K3, which are required for the undesired reaction of amino acid insertion. First, you have to deprotect your FMOC group. Then you need to wait for a coupling of your amino acid ester from the previous coupling step. So again, that K1 rate, that quenching of your amino acid ester from the previous step, is much, much faster than K2 and K3. So the end result is there's really no risk of insertion. And we prove this thoroughly with a variety of syntheses. So here in this first example, this is the JR Tenmer. And so as comparing Liberty Blue to Liberty Prime, we see comparable purities. However, and in taking a look at the chromatograms, we see very similar profiles. And we see that we can produce this peptide, this Tenmer, in only 25 minutes on the Liberty Prime, using half the amount of wash solvent, less than 50 mils, and producing less than 100 milliliters of waste. So this is dramatic improvement to throughput for the system while maintaining or improving purity. Here in this example of the ABC 20mer, again, we're going to take a look at comparing Liberty Prime to Liberty Blue. So this is a combination of our Carbomax methodology and the rapid one-pot coupling deprotection to our high-efficiency process that's already established and well-vetted with the Liberty Blue. We see, again, comparable purities, comparable chromatograms, but half the synthesis time, dramatic reduction in wash solvent, and also total waste. So let's try some more difficult sequences. Here's, again, a pharmaceutically relevant one, glucagon. Synthesizing glucagon, we can see a nice chromatogram, good synthesis with a clear product peak. Here on both the 0.1 scale and also the 0.2 scale, we see that this is even a scalable method. So we can scale up to a larger scale synthesis, still in a dramatically rapid time, so only about 2 hours for the synthesis of 0.2 millimole scale for glucagon. And we can do it in very high purity. Comparing the mass specs, we see great results from both of them. And this was something that was just synthesized simply on a polystyrene Wang resin. So to expand our scope of peptides that we're looking at, we wanted to examine a couple more difficult ones. So exenatide, GLP-1, these are both pharmaceutically relevant, as well as conotoxin and also the Z domain of protein A. So these are a couple different sequences, some shorter chain but still difficult, some longer chain, varying difficulty. And we see that we can synthesize them very, very quickly, all of them in less than 2 hours, all of them less than 300 milliliters of waste. And the chromatographic results look great. So we see single discernible peaks, we see clean mass specs through all the sequences, and I do want to mention for the conotoxin, so the bottom left chromatogram, PNI1, this is a shorter sequence, so on our mass spec it actually sees more fragmentation, so that might look a little bit dirtier, but that's just from the fragmentation of the actual mass spec since we have it calibrated for long sequences. And these results really are impressive to see, very rapid production. So GLP-1 produced in only an hour and 14 minutes, producing only 200 mils of waste, and with that kind of purity on the peak. But we weren't content with just looking at standard sequences. We now wanted to examine some more difficult peptides. In this case, we're going to take a look at N-methyl-containing peptides. So on the Liberty Prime, we've produced these 5 different sequences, all very, very rapidly, about a half an hour synthesis time for all of them. About 80 mils of waste for all, and crude purities in excess of 80% in all cases. So in addition for these sequences, we decided to challenge ourselves even further. In addition to obviously difficult N-methyl-containing peptides, we decided to use a higher loading, 0.75 millimole per gram ring gamut MBHA polystyrene resin to really demonstrate the power of this system. And so here I'll take our best case and our worst case. Get to look at what we consider to be, good and also more difficult, but still great. And in this example, for sequence 1, we see, again, a very clean peak, nearly baseline resolution, synthesis time of only about half an hour, and again, great purity, 91% purity out of the sequence. And for the most difficult sequence we made, this sequence number 3, we still see a very clean product peak, even zoomed in. You can see the bottom chromatogram is the expanded chromatogram to make sure that you can see all the purities. We see a great fast synthesis, 33 minutes, very, very efficient production, and great product peak overall. Next, we're going to take a look at an area of research which has grown in interest in recent years, cyclotides specifically in this case, on the Liberty Prime. And so these are very, very difficult sequences traditionally. What we're going to do is in the following slides, we'll be producing just the linear sequences. We did take them on for cyclization and for disulfide bridging later on. But the results that we're interested in right now for this presentation are strictly the linear ones to see how efficiently Liberty Prime can produce these peptides. And so we see this is just a couple examples. I have quite a few more, but no need to bore you. In just these 4 examples, you can see very successful synthesis of these sequences, clear product peaks, and the other sequences were also produced in comparable purities. All sequences were produced very rapidly, about an hour to an hour and a half at most synthesis time, and also very efficiently, less than 300 mils of waste in all cases. So we're really challenging ourselves here with many different sequences, pretty much the whole gambit of what you could want to produce in a production lab. And finally, we're going to take a critical look at another area that's received a lot of interest, the personalized medicine market. So taking a look at making peptide vaccines for use in various applications. In this specific case, we're going to take a look at cancer vaccines. And the need to produce these peptides in very high purity and also very, very quickly to fit in with the workflow of the personalized medicine market. In our case example here, we took from this breast cancer research paper a series of 14 different peptides that were produced in the paper, and we reproduced these syntheses on the Liberty Prime, looking to maximize our high throughput needs and produce them on a relatively large scale, so a 0.4 millimole scale. So each of these peptides were produced at the 0.4 scale, and you see the purities here, but purity percent doesn't say the same thing as chromatograms. And so here in these chromatograms, you can see very, very clean, clear product peaks, baseline resolved, and all of these 14 different peptides were produced extremely rapidly. Only about 12 hours and 15 minutes, only about 3 liters of total waste produced. So the Liberty Prime is capable of producing high throughput peptides very, very fast and very efficiently with high purity. The unique nature of a fast sequential process also offers a number of benefits over parallel processes which are typically used right now. You saw from all of the previous slides for the entirety of this presentation, the high crude purity of peptides that are produced by a fast sequential process where you have complete control over all reaction parameters. These single peptides are produced extremely quickly, and as soon as they're produced by the system, they can be taken off of the resin sampler or the resin loader and cleaved, analyzed by HPLC and UPLC. So purification can begin as soon as the sequence is completed. There's no need to wait for other sequences to complete, and there's no need to just hang around and wait for a large batch. In addition, they're produced very, very effectively, so much less waste is generated, meaning that labs are saving a lot more on acquisition costs because there's no reason to buy a lot more DMF or wash solvent than you actually need, and also on disposal costs because you're not producing as much waste. So really, we see that a high throughput is achievable with this sequential process because it's easy to produce 24 difficult peptides, as we've seen, sequentially in only 1 day's time. This is because of the power of the Liberty Prime cycles. So I've taken both a smaller scale and a larger scale here. We've got the 0.1 millimole scale on the top, and here we see that you can produce a peptide, again, or rather couple an amino acid on, every 2 minutes and 10 seconds, producing only about 8 mils of waste. On the larger scale, it's going to look more like about a 4-minute cycle time, so about 3 minutes and 50 seconds for every cycle or amino acid residue addition. And as far as your volume, you're only producing about 25 mils of waste. So if you take this cycle comparison and extrapolate production of 24 different peptides on the system. We can look at producing about 4.8 grams of peptide, on the smaller scale, in only about 20 hours. So again, just less than a calendar day, you can produce these 24 different 20-mers in great purity, very efficiently, using only about 2 liters of wash solvent and only producing about 6.3 liters of total waste. On the larger scale, again, this is now almost 20 grams of peptide that you can access. Very, very fast, about 35 hours total time, and producing less than 15 liters of waste. So besides this high throughput capability, the Liberty Prime is also capable of scale-up. This can be done very simply by pooling consecutive batches that are synthesized on the Liberty Prime. So in this next experiment, what we're going to do is take a look at producing 10 grams of crude peptide simply overnight. So imagine you end of your workday, queue up various positions on the Prime system. When you walk in the morning, you have 10 grams of peptide, high-purity peptide waiting for you. So this, again, as I mentioned, is coming from pooling of consecutive batches on the Prime. This is a multiple automated repeat format run at the 0.5 millimole scale. Cycle time is only about 4.5 minutes. And so you can produce about 1 gram of peptide, 1 gram of about a 20-mer, every 90 minutes. That's done using this wide variety of different reaction vessels that we have. So again, on the smaller scale, you would use that 30 ml reaction vessel over on the left-hand side. For the large scale, it's possible to use the 50 ml in the middle or even the 125 ml reaction vessel all the way on the right-hand side. So in this study, we're going to look at making a difficult sequence, the beta amyloid sequence 1 to 28. Again, as I've mentioned, the synthesis scale will be 0.5 millimole. We're going to perform 6 consecutive runs and pool the batches. Overall runtime of one sequence is about 2.5 hours. That means the whole study is done in about 14 hours. So importantly, we use a very low coupling excess, only about 3-fold excess of amino acid, and the total waste produced is only about 8 liters. Taking a look at the results, we see very, very clean, or very good-looking chromatograms, rather. So we're able to produce this 10 grams of crude peptide in only about 15 hours. This is about and this also, you can see, very high consistency and quality batch to batch. So it's a very reproducible process between the multiple different syntheses. Again, we do this with only about 8 liters of total waste and only 3 equivalents of the FMOC amino acid used. So the Liberty Prime really suits any production need. If you have a high throughput lab, you have the need for 20 mers, that you're producing, or any type of variety of sequences, you can produce these less than an hour. So 20 mers produced about every 45 minutes, and only about 8 mils of waste is produced per cycle. Plus, you can automate this process to produce up to 24 peptides completely unattended. In addition, the Liberty Prime definitely allows some scalability for your process. So in that previous study for the beta amyloid 1 to 28, we saw that we can produce 10 grams of peptide in less than 15 hours with extremely high batch-to-batch reproducibility that allows you to pool syntheses to create a larger throughput for your desired sequence. In conclusion, we see that microwave SPPS is really a critical tool for industrial peptide production. We also see that it's dramatically faster, 15 times faster than initial microwave technology. So this combination of fully optimized, or pre-optimized really, carbodiamide coupling strategy, which is robust for a wide variety of different sequences, and coupling it to rapid fluid handling and very efficient and advanced hardware, we see that we can produce a high throughput peptide need, also scale up peptide needs very, very quickly. Now, something which we didn't discuss in this presentation, but you can always contact us for more information on, is the ability to then take this process and scale it up even as large as 17 liters with one of our scale-up synthesizers and use the entire process, both the prime and also the scale-up system, as part of a GMP in a GMP lab. So ultimately, microwave SPPS really provides a unique value for efficient synthesis of peptides when it comes to the purity of product, the speed of production and throughput of production, and the efficiency of waste generation. I'd like to thank you very much for your attention, and also thank and acknowledge the amazing team of chemists and engineers that we have here at CEM, which made not only this research possible, but then the amazing instrumentation coupled to our chemistry developments to provide the best tools for synthetic chemists out there. So if you want some more information, I'd recommend visiting our website. In the U.S., you can contact your territory sales manager, Greg LeBlanc, at the email address seen here. If you just have general questions, you can always contact info@cem.com. And also now I'd like to open the floor to questions, and thank you very, very much for your attention.
All right, thank you, Michael. So we'll go ahead and take a few questions at this time. Just a reminder, please be sure to type your questions into the answer box on your GoToWebinar panel. We might not be able to get to all questions, but please still send them in and we'll answer by email following the webinar. All right, so our first question is, do you have any examples of glycopeptide synthesis and their purity, and what are the coupling times for glycoamino acids?
Yes, that's a good question. We actually do have, I believe we have a few examples of multiple glycosylated residues. As far as the methods that we used, off the top of my head, I'm not entirely sure, but I'm pretty sure they were effectively the same as the existing Carbomax methods with that double DIC and using that little bit of DIA, that 0.4 equivalent of DIA for stabilization. But we'll follow up directly with the person who asked the question and provide you with any of the synthetic data we have.
All right, so another question we have is, what is the maintenance required for the Liberty Prime pump?
So to be honest, and I know I stated this a number of times, I'm not trying to be too repetitive, but there really is no maintenance involved in the pump. So the pumps are pre-calibrated from the factory. We set the calibration here, and then they deliver consistently that 0.25 volume increment for every stroke of the pump, pretty much. So there's nothing necessary in terms of moving parts that need to be maintained. We have some filters that are on the supply lines, which those can be replaced periodically if you see some discoloration or anything like that. But the pumps themselves don't require any additional calibration or input like that.
All right, so next question. Am I still able to run room temperature methods?
Yes, actually, it's possible to do that. I mean, I know the predominant, all the research that we presented was really mostly heated synthesis because by and large that provides the best results. But I know for some sequences, whether they be special monomers that people may have that they're using that are temperature labile, that they need to use room temperature deprotections or couplings, or they want the entire method to be room temperature. Yes, it's possible to use these room temperature methods on the Liberty Prime system.
All right, and another question we have here is, I already have a Liberty Blue. Can I upgrade to the Liberty Prime?
Yes, it's possible to upgrade to the Liberty Prime. So we have a number of different unit configurations actually that are possible. So existing Blue customers can add on the pumping module and make the internal changes to their Blue system to run like a Prime, and then run these rapid methods with or without auto samplers too. So it's possible to have the auto samplers on it if you have, say, an HT12 system or even an HT24, and you can add the pump at a later date, or you can just add the pump to an existing Blue system and then reconfigure the system to run it.
All right, this next question is asking about different reaction vessels. So do you need different tubing for the 50 mil RV versus the 30 mil, or is that quickly interchangeable?
No, you don't need different tubing. The 50 and the 125, both of those larger sizes, just fit right into the same attenuator assembly that uses the 30 mil and also use the same drain line connection. So it's just a direct drop in.
All right. Next question is, does the pump module require external nitrogen source?
It does not. So the pump is actually, I believe technically it's a cantilever type pump, but the whole point is that it doesn't need any kind of pressure or anything to move liquids around the system. The pull and the push is generated by the actual pump motion itself. So no, there's no extra nitrogen or other types of requirements that are necessary. It just needs to plug into a power source.
All right. Next question is, can I use the new chemistry methods on the Liberty Blue? Liberty Blue.
Yeah, actually, so the Carbomax methodology that we had discussed, that's possible for use on the Liberty Blue system, and really, honestly, with any type of peptide synthesis protocol. It's the basic addition of using that extra DIC. We've seen great benefits across the board, as you'd see from most of the data. and really no detrimental effects. So it's something that right now very easily just doubling your concentration of DIC can provide that faster oasyl isorurea formation. And then the addition of that DIA for some of those acid sensitive sequences or moieties rather, it provides a great benefit there too. So yeah, go ahead and get started right now using it.
All right, and our last question here is, what is the stage of the system to be validated under GMP?
So that's actually a very good question, and one that we do receive very often when it comes to this system, the Liberty Prime, or our scale-up system, the Liberty Pro. Now, at this point, the Liberty Prime does not have some of the software permissions required for GMP, but we are currently implementing that to ensure that we have full traceability of various user logins, changes to settings and methods and stuff like that. We also do have, as I'd mentioned previously, these certificates of line clearance and validations for no cross-contamination, which is also an important part for establishing good SOPs for GMP. So right now, I would say we are very, very close, probably only a few months off from having all the paperwork together and everything necessary for a convenient implementation into a GMP facility or a lab.
All right, great. Well, if there are no other questions, thank you, everyone. We appreciate you being here for this webinar. As Michael mentioned, please visit the CEM website for more information on our new chemistry methodology and the new Liberty Prime Peptide Synthesizer. While you're there, check out the latest application notes from the peptide synthesis group, as well as the peptide synthesis reagent store. So right now, if you look down on the download section of your screen, you'll see a couple of our application notes with today's mentioned new chemistry methods and the Liberty Prime instrument. I've also included our complete reagent list for you, those of you who have questions about resins and amino acid offerings that CEM has. So thank you again for joining us, and we hope to see you next time.